Okay, hi everyone. Can you hear me?
I
Yes.
can hear you all right.
Okay,
All right,
cool.
we're muting the room because we don't want any crosstalk. So when you
Got
ask
it.
that, I just muted us.
Okay, awesome. Yeah, so hi everyone. Like we introduced ourselves earlier, my name is Bryn Bailey, and this is my colleague Sasha Cohen. We're both planetary defense researchers in the physics department at UC Santa Barbara. And this is our, I think, third PCC. It's, as I said earlier, our favorite conference to attend. We're really bummed we can't be there in person, but happy to be here remotely. So hopefully next year we'll be sitting there next to you. But either way, thanks so much for giving us the opportunity to talk to you today about Pulverize It or PI, which is our multimodal planetary defense study currently in phase two of NASA's Innovative Advanced Concepts program. I know we've given a talk about our project for these last 3 years. So today, the two of us will take turns talking about specific aspects of the program, starting broadly with a discussion of the methodology, and then focusing our attention on simulations of hypothetical mitigation for asteroid 2024 YR4. Next. So, of course, space debris entering Earth's atmosphere is not uncommon and usually consists of small bodies or fragments of bodies that are generally not considered threats. But on occasion, we may be visited by larger objects that do have the capacity to enact damage. In practice, we've seen that kinetic impact is a tried and true method, as the DART mission showed us in a tremendous breakthrough for planetary defense, though presently deflection is the only method which has been reliably put into practice. And in a real mitigation scenario, a deflection mission hinges largely on time. An object's discovery must give us enough time to design and launch a mission to deflect it relatively far ahead of its impact, which is on the scale of years, if not decades. And while most NEOs are small and non-threatening, there's always some possibility that something bigger could come by or that we don't see an object far enough ahead of time. And for some perspective, we can look kind of as Mark was just discussing to the Chelyabinsk airburst of 2013 and Tunguska in 1908, which both serve as examples for our need for both detection and mitigation efforts. So to give a little bit of background more about Chelyabinsk, at 18 meters in diameter, this released an estimated impact energy equivalent of around 500 kilotons of TNT. It caused damage out to 120 kilometers from the supersonic path, shattering glass in over 3,600 buildings and resulting in over 1,000 injuries. And objects at least the size of the Chelyabinsk asteroid are expected to impact Earth about every 50 to 100 years. And larger than this, as we just heard, was the Tunguska airburst, with an estimated impact energy between 3 to 15 megatons. And we heard that the resultant shockwave flattened a large portion of the surrounding forest. I'm not going to name any numbers. Um, and objects similar to Tunguska are expected to impact Earth every 300 to 1,800 years. Next. So as a more recent example, and the main subject of this talk, we have Asteroid 2024 YR4. This being a conference about cratering and NEOs, I don't have to explain much. It was our job to be glued to this news in late 2024, early 2025. But for those maybe playing along at home, 2024 YR4 was discovered on December 27th, 2024, 2 days after its closest approach to Earth, in which it came within about 2 lunar distances, which is very close, but not the closest it's ever going to get. That title goes to its approach in 2032 on December 22nd. And the all-important question, is it going to hit us? Next. No, but we once thought it might. Next. In January 2025, 2024 YR4 reached a record Torino scale impact rating of 3, meaning at the time it was estimated that there was a 1% chance that the object would hit us. The probability of Earth impact continued to rise, peaking at about 3% in February 2025, before eventually being reduced to 0 upon more and better observations. Then we thought it might impact the moon and stir up some different trouble, but we now know that isn't going to happen either. As for its physical characteristics, the object's diameter is estimated at about 60 meters, which, for perspective, is roughly in the ballpark of the Tunguska impactor's estimated diameter. If instead an Earth impact were to occur in 2032, which again, it won't, the collision could yield an impact energy of roughly 7 megatons, approximately 14 times the energy of the Chelyabinsk airburst, and comparable to Tunguska. In a scenario where the impact probability doesn't go down, where we would only have a few years of warning before disaster strikes, or in a situation with even less warning time. Next. What could we do about it? Or, sorry, one more time. Next. Okay, there we go. What can we do about it? What are our options? Do we have a system set up to handle not only distant, long-standing threats, but also threats that may require more immediate action? So current planetary defense strategies are not well equipped to combat a wide range of threat scenarios, particularly in the short warning regime where there's little to no time before impact. To achieve an extensive planetary defense system, it's imperative that we're prepared for a wide variety of threat scenarios that considers a large range of threat sizes and warning times to prepare us for anything. So that begs the question. Next slide. Can we append existing planetary defense strategies with a new approach that can provide reasonable mitigation of a wide variety of threats, including those in the short warning regime? And with that, I'll pass it over to Sasha to discuss the impact logistics.
Thank you, Bryn. We'd like to propose that the answer to that question is yes. And so I'll talk about how our planetary defense concept, which we affectionately call pulverize it or PI, how it works. So pulverize it works by coupling the kinetic energy of a hypervelocity penetrator into an asteroid target via shockwaves and material vaporization. The shockwaves generated by the impact damage material and crush porosity, which reduces the overall cohesion of the object. Over the duration of a few seconds, the asteroid is disrupted into a cloud of fragments, which disperses at a speed much greater than the gravitational escape speed of the parent object. So there's no possibility that the fragments gravitationally recombine afterwards. In most cases, this is where the story ends. The fragment cloud disperses until it has a diameter much larger than the Earth, which ensures that only a tiny fraction of the fragments, if any, actually intercept the Earth. However, PI can also operate in a terminal mitigation mode. In this mode of operation, the fragments are limited in size to less than 10 meters in diameter, such that they airburst in the Earth's atmosphere at high altitude, dispersing the total impact energy. And you'll hear more about this when I pass it back to Bryn. In order to simulate hypervelocity impacts, we make use of the hydrocode ALE3D, developed by Lawrence Livermore National Laboratory, and we run this code using NASA's HECC, or the High-End Computing Capability, and I'll skip over the details here. But in general, we run this code largely in parallel using NASA's supercomputers. Next, I'll provide an outline of our ALE3D simulation setup for hypervelocity impact simulations. Our baseline penetrator is a 10-to-1 aspect ratio tungsten cylinder with 750 megapascal yield strength. We use this penetrator as a baseline for comparison across simulations, but other penetrator geometries are being investigated. Although for the purposes of this talk, whenever I refer to a penetrator, unless I specify a different mass or aspect ratio, we're referring to a 10-to-1 aspect ratio penetrator. We use a two-phase Livermore tabular equation of state for granite as our baseline asteroid material, though future work will expand this into more realistic materials like olivine. And the asteroid material has a grain density of 2.6 grams per cubic centimeter and a porosity ranging between 40 and 50%. For the disruption simulation shown in this talk, we model our asteroids as weakly bound rubble piles, as shown on the left. Asteroid models are constructed by randomly packing granular boulders within a weak binder material. The binder material has an average strength of roughly 25 pascals, which is a value we will motivate on the next slide. Not only does the material yield strength vary from boulder to boulder, but we also vary the yield strength within each individual boulder using the Weibull strength distributions shown on the right. This allows for realistic simulation of fragmentation dynamics in geological materials like those simulated here. While we conservatively model individual boulders as having strengths as high as 250 to 500 megapascals, the cohesive strength provided by the binder material between the boulders is set to be much weaker. This is informed by measurements of asteroid rotation rates, which suggest that most asteroids above 100 meters in diameter are loosely bound rubble piles. Recent missions to asteroids like Bennu by the OSIRIS-REx mission and asteroid Ryugu by the Hayabusa mission also reveal loosely bound rubble pile-like surfaces. While this doesn't inform us about the interior structure of these objects, we can make generalizations based on observations of asteroid rotation rates. In this simulation, we show the robust disruption of a 50-meter diameter rubble pile asteroid model using a single 100-kilogram tungsten penetrator, impacting at 20 kilometers per second in the asteroid frame of reference. A brief analysis of the fragment statistics after impact shows that the average velocity of the fragments, shown by the red histogram on the left, is almost 3 orders of magnitude larger than the gravitational escape speed of the parent asteroid, shown as the vertical red dashed line. We also see that the specific impact energy, defined as the penetrator kinetic energy per unit mass of the target asteroid, is over 200 joules per kilogram. Previous work by Martin Jutzi and collaborators in 2023 has suggested that the limit for catastrophic disruption for sphere-on-sphere impacts is roughly 100 joules per kilogram. While not a direct comparison to penetrator impacts, we still see that exceeding this threshold does indeed result in robust disruption. These results suggest that a single 100 kilogram, 20 kilometer per second penetrator, or an equivalent specific impact energy over 200 joules per kilogram delivered below the surface, is sufficient to mitigate a 50-meter asteroid, with the use of additional penetrators showing similar results for larger objects. This means that payload capacities of pre-existing launch vehicles, such as a SpaceX Falcon 9 or similar, can be used to provide a single launcher solution for objects in the 20 to 150 meter diameter range. In this simulation, we show the robust disruption of a similar 50-meter diameter rubble pile asteroid model, but with 5 separate 100 kilogram penetrators in a plus shape, so with one to the north, one to the south, and then to the east and the west, as well as one in the center. The histograms indicate the distributions of fragment masses, shown in orange, fragment diameters in meters, shown in blue, and speeds in meters per second, shown in green. The red histogram, corresponding to the right axis, shows the original boulder size distribution within the asteroid. When compared to the blue histogram of fragment sizes 10 seconds after impact, it can be seen how the initial boulders have been largely reduced into fragments with an average diameter of roughly 1 meter. So instead of just flinging out the boulders that pre-existed in the asteroid, we're actually pulverizing those boulders and then flinging out the fragments. As in the previous case, the green histogram of fragment speeds shows how the average fragment speed is over 2 orders of magnitude higher than the original gravitational escape speed of the object. The inset plots at the bottom right show the material damage parameter D, which scales between 0 and 1, 0 representing undamaged material and 1 representing fully damaged material, which no longer retains its tensile strength. As can be seen, near complete volumetric material failure is achieved in this case. As a comparison to the previous simulation that I just showed, this one condenses the 500 kilogram mass into a single penetrator. The results show that a single penetrator case succeeds in transferring approximately 2 times as much of the initial penetrator kinetic energy into the target as the 5 separate penetrator case shown on the previous slide. This is likely due to the increased penetration depth of the single penetrator, which allows for better kinetic energy coupling. As before, when compared to the blue histogram of fragment sizes 10 seconds after impact, it can be seen how the initial boulders have been largely reduced into fragments with an average diameter of roughly 1 meter, indicating that we are, instead of merely disassembling the pre-existing boulders, we are actually first pulverizing them and then flinging them out, as I said before. It should be noted that in reality, there would be a large skew to the fragment size distribution to much smaller fragment sizes, but these are not resolved in our simulation since we use a finite mesh resolution. In addition to robust disruption, Pi can operate in alternative modes depending on what is required to mitigate a particular threat. The first is an induced rocket mode, wherein material rapidly ejected from the entrance cavity can induce a significant amount of transient thrust. This is common to all hypervelocity impacts with a high aspect ratio penetrator, and the induced thrust can be compared to a heavy launch vehicle for a short period of time. The second alternative mode is an enhanced deflection mode, wherein an asteroid is fragmented partially or asymmetrically, and can induce enhanced momentum transfer via a very large momentum enhancement factor due to its significant ejecta. This momentum enhancement factor is commonly referred to as beta, as I'm sure everyone here is familiar with. An example of the enhanced deflection mode is shown here for a 500-meter rubble pile asteroid model. In this case, a 10 metric ton penetrator impacting at 20 kilometers per second can induce a beta as high as 80. This is evidenced by the significant amount of high-speed ejecta shown in the density and speed plots here shown here. The density plot is on the left, and the speed is on the right. As an additional example of the enhanced deflection mode of operation, we show a 1 kilometer rubble pile asteroid model. In this case, a 100 metric ton penetrator impacting at 20 kilometers per second can induce a momentum enhancement factor as high as 40, illustrated in this plot of the fragment speeds. And I realize I'm kind of flying through this before the simulation actually gets a chance to play fully, so I'll let this go through once and then continue on. In order to better understand the internal dynamics of a penetrator during impact, we ran a series of high-resolution 2D axisymmetric simulations with 500 kilogram penetrators. The target in this case is a long slab of asteroid material with a 50 to 100 megapascal Weibull yield strength distribution and 40% porosity. The plots at right show density and pressure for a 10 kilometer per second impact. Note how the ratio between the penetration depth and the length of the original penetrator, often referred to as P over L, is slightly above 3, and that's a value to keep in mind as I go on. In this series of plots, we show how the impact pressure is distributed in the right column and how the plastic strain is distributed within the penetrator in the left column. The maximum of the pressure color scale at right is set to 750 megapascals to illustrate regions which exceed the penetrator yield strength. Regions in yellow meet or greatly exceed this value, with the maximum pressure observed at any given time ranging between 60 and 65 gigapascals at the front of the penetrator. These plots similarly show density and pressure, but for a 20 kilometer per second impact. Note how the ratio between the penetration depth and the length of the original penetrator, again P over L, is also slightly above 3 and not significantly improved over the 10 kilometer per second case. This is expected close to the so-called hydrodynamic limit, where material strength becomes somewhat negligible compared to inertia, and materials instead behave more like fluids. Also note the frictional interaction with adjacent vaporized material, which is distinct from the 10 kilometer per second case shown previously. To illustrate this more clearly, we can show how the pressure in plastic strain is distributed as before. In this case, we can see how the back of the penetrator is exposed to significant plastic strain prior to achieving maximum penetration depth. This is caused by adjacent vaporized material being forced into contact with the sides of the penetrator, which ultimately causes complete material failure in the back of the penetrator earlier than maximum penetration depth is achieved. While this does not make a significant difference for a passive penetrator, it does play a significant role in designing mitigation scenarios where payloads are required to be delivered below the surface, as will be seen shortly. In order to better understand the internal structure of asteroid targets, or in order to enhance a particular mitigation scenario with a nuclear explosive device, or an NED, a set of instruments could be included as part of the penetrator payload. However, survivability of the instrument package until far below the surface becomes critical to ensure. These simulations show a 500 kilogram tungsten penetrator with a suspended mass acting as an instrument package analog, impacting an asteroid simulant target at 5 and 10 kilometers per second. These results suggest a sort of zone of survivability between 5 and 10 kilometers per second impact speed, where below 5 kilometers per second, the payload is subjected to impact forces early, since the impact speed is less than the phonon speed in tungsten, and where above 10 kilometers per second, the frictional interaction with adjacent vaporized material also subjects the payload to impact forces early. Within this range of 5 to 10 kilometers per second, it is conceivable that a hypervelocity penetrator could deliver an NED below the surface of an asteroid. We approximate subsurface NED detonation using a method similar to that described in Schroeder 1974, more commonly referred to as an energy pill. Radiation transport is not explicitly simulated. Rather, the simulation is initiated by injecting material into a sphere of subsurface material. The radius of this sphere in meters is determined by this approximation shown on the screen, where W is the yield of the device in kilotons of TNT equivalent. This method indirectly simulates the absorption of the radiative output of the device by pre-vaporizing a volume of subsurface material. This is an adequate approximation since the mean free path of high-energy radiation is relatively short, typically less than a few meters, within rocky materials. The energy injection heats and vaporizes the material within the prescribed sphere, generating a shockwave of similar magnitude as that produced by an NED. By removing the need to directly simulate radiation transport, this simplifies the methodology and allows coupling to hypervelocity impact models for simulation of subsurface NED delivery to a target. This simulation shows a close-up of an energy pill simulation, specifically a 1 kiloton yield delivered to a depth of roughly 6 meters below the surface by a 2.5 metric ton penetrator at 5 kilometers per second. The simulation on the left is actually a continuation in time of the simulation shown on the previous slide. And these show a comparison between a 1 kiloton yield delivered 6 meters below the surface, as before, which results in catastrophic disruption, and the same yield device detonated at the surface. The results show a significant reduction in coupled energy from the NED in the surface burst case, showcasing how even a modest depth of burst can result in greatly improved energy coupling. Future work will present simulation results for a variety of other impact scenarios, including close sequential penetrators for hole drilling and improved depth of penetration. Sequential penetrators with significant spacing are also being explored for purposes of delivering explosive devices below the surface. Finally, we're also working, I should mention in brief, we're also working towards studying asymmetries and moving away from idealized approximation of these cases. These are examples of off-axis penetrators, but I won't go into that in detail here, but these results are forthcoming. Oops. And finally, we're also working towards using actual asteroid shape models for our targets, which will allow us to explore a much more diverse variety of target shapes. With that, I'll turn it back over to my colleague Bryn to talk about ground effects. Thanks.
Okay, awesome. Thanks, Sasha. Yeah, so now we're going to move away from the impact stage and talk about what happens afterwards. So pi represents a versatile multimodal approach that could be used in a wide variety of scenarios, whether the warning time is on a scale of weeks or years, or for threats like Chelyabinsk or like Apophis. In longer warning scenarios, where an impact is months or years away, the fragments can miss Earth entirely, completely removing the threat. And depending on an asteroid's size and speed, short warning mitigation scenario could be feasible. In these short timescale intercept scenarios, which we refer to as terminal scenarios, the fragment cloud would enter Earth's atmosphere, where it would disperse the energy of the original asteroid through spatially and temporally decorrelated ground effects. Of course, PI's preferred mode of operation is in the extended intercept regime, where we could intercept an asteroid far ahead of its impact. So it's preferable for any method of planetary defense to be used far ahead of time and as early as possible to keep the aftermath away from Earth. Though our findings do suggest that Pi is uniquely capable of operating in this terminal mode in certain scenarios where the factors are favorable. So in the terminal mode, during atmospheric entry of the fragments, the pressure exerted by the atmosphere eventually exceeds the fragment's material strength, causing a cascading breakup event. And as pressure and heat increase, the fragment ablates and the material fails, causing the fragment to burst. Collectively, these bursts produce optical flashes and decorrelated shock waves on the ground. These optical and acoustic ground effects spatially and temporally distribute the energy of the original asteroid, which, in reasonable mitigation scenarios that are appropriate for the threat, result in little to no damage. We design our terminal scenarios to keep the ground effects below reasonable thresholds to prevent high-level damage from occurring. For the acoustic effects, we aim to keep all shockwave overpressures below 3 kilopascals, which is the point at which residential windows may begin to break. And for the optical effects, we aim to keep the cumulative optical energy below 200 kilojoules per square meter, above which organic materials like paper or grass may begin to catch fire. Next. Okay, so here we simulate the acoustic ground effects in a very terminal mitigation scenario for an estimate of asteroid 2024 YR4. Both boxes are looking at an asteroid that is 60 meters in diameter with an average density of 2.6 grams per cc and an exoatmospheric velocity of 17.1 kilometers per second, which is the estimated velocity at atmospheric entry if an impact were to occur during the object's close approach back in 2024. So in the left box, we disrupt the body into 4,000 fragments one day before Earth impact, and in the right box, we simulate an equivalent unmitigated asteroid airburst. The upper movie plots display the real-time pressure, and the cumulative distribution functions on the bottom show the frequency of occurrence of various pressure values. And to note that in the fragmented case, the simulation does include constructive interference from overlapping shock waves. In the fragmented scenario, we achieve an average pressure of about 1,200 pascals and a rarely occurring maximum pressure of about 2,200 pascals. So at no point during the simulation do we reach that 3 kilopascal limit. We also pay special attention to the value that occurs at 1% of the cumulative distribution function, which is the value that 1% of locations on the ground within the observation area experience. And here we see a 1% CDF value of about 1.4 kilopascals, a little less than 50% of our threshold value. Conversely, the unfragmented case has an average pressure of about 22 kilopascals and a maximum of 41 kilopascals. And let's address the elephant in the room. The mitigation scenario on the left is an extreme worst case scenario. This is simulating a hypothetical in which we would have discovered YR4 several days or weeks before its initial close approach in December of 2024, assuming operational status could be quickly achieved. But we would never want to do this if we don't have to. It's always preferable, as I mentioned earlier, to use any planetary defense strategy as far ahead of time as possible. But with cases like 2024 YR4's late discovery just after its closest approach, it's reasonable to imagine a situation in which we would have very little warning. And we show these extreme results because even with minimal warning, they suggest that Pi can be effective in terminal mitigation of smaller objects, and combined with detection efforts could potentially prevent events like Chelyabinsk or Tunguska in the future. Next. As for the optical effects, here we're looking again at the 60-meter asteroid cases, with the fragmented case on the left and unfragmented on the right. The fragmented case has an average optical energy deposition of about 11 kilojoules per square meter, a 1% value of 26.1 kilojoules per square meter, and a maximum of 26.4. Whereas in the unfragmented case, we calculate an average optical energy of about 2,500 kilojoules per square meter, a 1% value of 11,000, and a maximum around 18,000. So we see again that this disruption works to dramatically decrease the optical energy flux to manageable levels. And I think in the interest of time, I'll skip these next two slides and just kind of start wrapping up. Okay, perfect. I'll go through this one quickly. So to kind of wrap up everything we've been discussing, we've also begun a mission design effort in which we're looking into feasible objects for an actual disruption test. For now, we've narrowed our focus on objects within the 30 to 140 meter diameter class, limiting our current scope to objects which can be reasonably disrupted with a single launcher, using that kind of single launcher solution, which would greatly decrease complexity. Our preferred starting vehicle is the SpaceX Falcon 9, which is typically what we use in our impact simulations, as Sasha was discussing, but we're open to exploring different launch vehicles. And additionally focus on objects that have a close approach distance within about 0.1 AU within the next 10 years or so. And we narrow our query further to minimize the C3 required at departure and maximize delta V in hopes of impacting the target at high velocity. We're especially interested in designing a mission to 2024 YR4 as it is of such high interest. We're currently working with our partners on mission design and analysis, including groups from JPL and UC Colorado Springs. And if anyone here is interested in or knowledgeable about mission design, please come talk to us. We would love to talk to you. We're always open to collaboration and love hearing from others in the community. Next slide, please. So to conclude, PI represents an effective multimodal method for planetary defense that could prove useful in a wide range of threat scenarios, spanning both asteroid size and warning time, up to existential threats. It represents the first planetary defense strategy that is capable for use against short warning threats and allows for a logical roadmap toward a robust planetary defense system, creating a single launcher solution with at-the-ready capability. Thank you all so much for your time, and we'd be happy to take any questions if you have any.
Thank you both so much. That was a really great talk. Does anyone in the room or online have any questions? If you're online, feel free to either raise your hand or type it in the chat and I'll read it out. While folks are thinking, I do have a kind of a granular modeling question. I was wondering about the choice of resolution in your models and if you've done any kind of resolution for test reviews and whether you see changes in fragmentation with any kind of resolution testing, how that informs your choices.
I missed the middle part of the question. You asking about the mesh resolution in the disruption simulations?
Yes, yeah, and how you choose your resolution and if you had to do resolution convergence tests.
Yes, good question. Thank you. So we couple two different simulation types to span the full time range of what we'd like to simulate. In the early timescale simulations, we use a ratioed mesh where the mesh resolution is very high, very near the impact site, and then reduces in resolution as we go out. And then that simulates the very early timescale out to about 1,000 microseconds, and the mesh resolution is sub-cubic centimeter, local to the impact site. And then we couple the output, the end result of that simulation, to a much coarser mesh resolution simulation, which allows us to extend the simulation out to macroscopic timescales. And typically, the mesh resolution in those longer timescale simulations is about cubic meter, roughly. And that's why our fragment size distributions stop at about 1 cubic meter on the small end.
Great, yeah, I was definitely wondering about how that affects your fragment sizes. Thank you.
Yep.
We have a little bit of time for one last quick question, if anybody has anything quick. All right, if not, then thank you both so much. Really cool to get some insight into these models.
Thank you so much.
And we'll go ahead and there's a really quick question in the chat. We have like 30 seconds about the radiological effects. If you can comment on that while we switch.
Sure. Coming from Sasha Egan, who's just trying to poke the fire. Yeah, we have looked into nuclear mitigation strategies, and we're currently working on a long-standing paper. We've been working on it for over 2 years, looking at the radiological effects of nuclear mitigation. So it's actually just been submitted to a journal. I submitted it about a week and a half ago. So hopefully at next year's meeting, I'll have a link to provide if that paper gets published. But yeah, keep an eye out from us if you are interested in hearing more about that. It's too dense to get into right now in the last 30 seconds of trying to answer questions. But yeah, we've got a really long, dense, complex, but good read coming your way. So keep your eyes peeled.